Hi, my name is Nadia Zaragoza, and I'm a materials science and engineering major at Georgia Tech. This summer, I did a project through the Texas A&M online O-REU program in collaboration with my mentors who are from Los Alamos National Lab, Blas Uberuaga, Enrique Martinez, and Ted Holby. This project is a part of the FUTURE program, which stands for Fundamental Understanding of Transport Under Reactor Extremes. My project was on atomistic simulations of iron-chromium interactions to inform thin film growth parameters. That probably sounded like a mouthful, but hopefully by the end of this presentation, you're able to understand what I was doing, why I stared at atoms all day, and why it was important. Let's get into it. So there's this cool new wave of nuclear reactors called fast reactors that are drawing increasing attention from researchers around the world because they have cool features like passive safety and fuel efficiency. But if we want to ensure the success of these reactors, we have to look at the materials that go into them and how they're going to respond to harsh conditions, especially radiation. Understanding and modeling how these materials behave in reactor conditions over time is essential to reactor design and safety analysis. An example of a structural material that goes into these reactors is stainless steel, which is often used for cladding. Iron-chromium thin films are being studied by researchers at Los Alamos because they actually serve as a good substitute for studying these stainless steels. And they've been irradiating these thin films and studying how the radiation will impact corrosion and material structure. But the process of growing these thin films is really complicated. In many cases, we want a single crystal film to study. Pure iron thin films have been produced with close to ideal structure, but adding chromium complicates that landscape. Because of the attractive forces between iron and chromium, the chromium atoms will stall the diffusion of the iron atoms in creating heterogeneous growth. Because of this, the experiments have required a higher applied temperature and applied electrical bias in order to get closer to the ideal structure. But the researchers want to be able to predict the ideal parameters that they need. What temperature do they need for different concentrations of chromium in order to produce that? And this is where LAMMPS, a molecular dynamics simulation code, can help us. By looking at what is happening at the atomic level, we can see how atoms are diffusing with different concentrations of chromium and get those ideal parameters. At the beginning of the summer, I developed a research plan for how I would progress through this project. I would start by creating test cases of pure iron structures, focusing on the 100 and 110 surfaces. If you're not familiar with that, that's just how the atoms are packed into the surface structure. And then I would add an extra atom and observe how that atom would diffuse across the surface over time, plotting the mean square displacement, and from there being able to get the diffusivity and the migration energy. Once I solidified that process of running simulations and extracting data, I was able to add different concentrations of chromium, and we also tested how different layers of chromium could affect the diffusivity. The end goal in all of this was to find a relationship between the chromium content and the migration energy, and this migration energy is what will inform those thin film growth parameters. To run these simulations, I would start by creating a BCC iron structure in LAMMPS and adding an extra atom. Then I would run the simulation for 10 million time steps, each 0.002 picoseconds. And I would run it for temperatures between 700 and 1100 Kelvin. This temperature range was chosen because it is high enough that there's still mobility in the atoms, but low enough that it doesn't get too close to the melting temperature, which for iron is 1800 Kelvin. Then LAMMPS will output a mean square displacement for each time step. Then I wrote a Python script that would plot the mean square displacement versus time, and hopefully that's linear because the slope of that is what gives us the diffusivity. From there, if I plot the log of the diffusivity versus the inverse temperature, the slope of that, which is also hopefully linear, will give us the migration energy. From there, I repeated that process for different concentrations of chromium in different layers to see if there is a trend. As I went through this process, we ran into several challenges. I noticed that plotting the 100 surface was pretty easy. The mean square displacement versus time turned out linear, got the diffusivity linear, pretty much linear, boom, got that migration energy. But I noticed that when we plotted the 110 surface, it was much more noisy. There were many peaks and troughs, and there was no way I was going to get a diffusivity without there being a ton of error. So I looked at the structures in O-REU, which is a visualization package. I noticed that there was a difference in the diffusion mechanisms between the 100 and the 110. In the 100, exchange occurs often, meaning that the way that the atom diffuses across the surface is by switching places with another atom, burying itself in the bulk and kicking out another atom. The green atoms in this video are all atoms that become an atom at one point in the simulation. And because of this, the reference point for the mean square displacement is constantly changing, and it adds up over time, and it becomes linear. Meanwhile, here in the 110, the surface structure is a lot more tightly packed, and so the atom doesn't diffuse by exchanging places with another atom. Instead, it stays the same atom the entire time and moves across the surface. Because of that, the mean square displacement is dependent on that initial starting position of that atom. And so as the atom moves away from the surface, the MSD increases, and as it moves back towards its original position, the MSD decreases. And that's what accounts for the peaks and troughs that we see in the graph. To correct for this, my mentors wrote a Python script that would reset the reference position for the MSD and allow it to accumulate over time, and also inherently calculate the diffusivity. And then, got them! The plots are linear. Many simulations later, I was finally able to plot the migration energy versus different concentrations of chromium, as well as migration energy versus layers of chromium for each surface. For the random cases in the 100 surface, we noticed an increase in the migration energy from about 0.7 to 0.9 eV. A higher migration energy means the atoms need more energy to move, so it has less mobility. Therefore, as the chromium concentration increased, the mobility decreased. We noticed in the layer tests that when we had the surface be completely chromium, the surface would, at the beginning of the simulation, immediately absorb the iron atom and kick out a chromium atom. So throughout the simulation, the atom was simply chromium. We noticed that the first two layers of chromium had significantly lower energy and therefore higher mobility. They also had a lot more error because, especially as temperatures increased, there was some effects like mixing of chromium atoms into the bulk. Sometimes there would be two atoms, and those would create inconsistencies in the diffusivity. After the first two layers, we noticed that having chromium in the structure increased the migration energy to higher than that of the pure iron case. We would expect that if deeper layers were tested, the values would eventually converge to the pure case. This indicates that having chromium in the surface increases mobility, but chromium in the bulk structure decreases mobility. The 110 surface overall had a significantly lower migration energy than the 100 as we predicted. The 110 surface was much more complicated at higher temperatures, tending to have a lot more error. This was again due to different effects like interlayer mixing, sometimes the surface would be sliding, and other effects that we still need to look into but would create inconsistencies in the diffusivity values. Because of this, we decided to fit our plots to the 700 to 900 Kelvin range, in which the data was a lot more consistent. We noticed that in the random cases, we saw more of a plateau in comparison to the 100. There was a bit of a dip at 10% and an increase for the 15%, but overall not a clear trend. Meanwhile, in the layer cases, we noticed an almost oscillating behavior, with higher and lower migration energies for alternating even and odd layers, which seemed to approach the pure case as the layers went deeper into the structure. We aren't yet sure what this means, but hopefully with further study, we could put a significance to what this oscillating behavior could be. In summary, we were able to study the two surfaces, 100 and 110, and collect data on the mean square displacement, the diffusivity, and the migration energy. We did this for multiple concentrations of chromium as well as different layers of chromium. We discovered different diffusion mechanisms between the two surfaces, the 100 having an exchange mechanism and the 110 not having an exchange mechanism. In the 100 surface, we noticed an increasing trend in migration energy with increasing chromium concentration. Meanwhile, in the layer cases for 110, we noticed that the first two surface layers would cause a decrease in migration energy, while the layers in the bulk structure caused an increase in migration energy. For the 110 surface, we noticed that there was more of a plateau with the random concentration of chromium cases. Meanwhile, we saw an interesting oscillatory behavior in the layer cases. Overall, I really enjoyed this project. I learned so much, and these trends in migration energy are really informative for the parameters that affect homogeneous thin film growth. And these thin films will in turn be used to study corrosion in stainless steels for nuclear reactors. The best source of energy. I hope you learned something from this video. Don't forget to smash that like button and leave a comment with some feedback. Thank you, and go Jackets!